What if books were rare treasures, whispered secrets among the elite? What if knowledge only moved at the pace of a slow hand, penning each letter one by one? What if the very act of reading was a luxury, reserved for the few who could see the tiny script on faded pages? The Middle Ages, from the 5th century to the 15th century, saw incredible shifts that pulled back the curtain on a world waiting to learn. Number 1. The Astrolabe. Imagine gazing up at the night sky, trying to make sense of the dizzying dance of stars and planets. For centuries, people tried to understand how the cosmos worked, but they needed powerful tools to truly unlock its secrets. Before the Astrolabe, astronomers relied on simple observations, often with the naked eye, sometimes with basic instruments like quadrants or armillary spheres. These tools were useful, but they lacked the versatility and precision that a truly revolutionary device could offer. Learning about the heavens was often a mix of observation and complex mental calculations, a challenge even for the most brilliant minds. Sailors, too, faced immense challenges relying on dead reckoning or the sight of familiar coastlines, making long voyages into unknown waters incredibly risky. The practical application of celestial knowledge was limited by the tools at hand. Then came the Astrolabe. It wasn't just a simple instrument. It was like a pocket-sized universe, a marvel of medieval engineering and mathematical genius. Its roots stretched back to ancient Greece, where astronomers like Hipparchus first theorized similar concepts. But it was in the Islamic Golden Age, starting around the 8th and 9th centuries, that the Astrolabe truly came alive and was perfected. Scholars in places like Baghdad and Cairo refined its design, adding new features and creating detailed instruction manuals. People like Muhammad al-Fazari, who lived in the late 8th century, are often credited with building one of the earliest known metal astrolabes in the Islamic world. Later, brilliant minds like al-Battani in the 9th century and al-Sufi in the 10th century wrote extensively about its uses, spreading its knowledge far and wide. This incredibly complex device finally made its way to Europe through Spain, specifically through the intellectual hub of Al-Andalus around the 10th and 11th centuries. Scholars there, many of whom were translating Arabic scientific texts into Latin, quickly grasped its power. People like Gerbert of Aurillac, who later became Pope Sylvester II in the late 10th century, was a keen student of Islamic science and is often mentioned as one of the first to introduce the astrolabe to Christian Europe after studying in Spain. His interest shows how eager European scholars were to embrace new learning. So, what exactly was this analog computer of the Middle Ages? At its simplest, an astrolabe was a flat disk, usually made of brass, with a rotating pointer called an alidade and several interchangeable plates called tympans or climates, each engraved with a different celestial grid for a specific latitude. On top of these plates sat a ret, a movable star map representing the fixed stars in the sky. By rotating the rete and the alidade, you could solve a whole host of problems related to time and celestial positions. It was like having a portable planetarium that could answer your questions about the universe. The Astrolabe revolutionized learning in multiple ways. First, it made astronomy a much more practical and accessible field of study. Students no longer just read about the stars. They could actively work with them. They could use the astrolabe to identify stars, measure their altitude above the horizon, and even track the path of the sun throughout the year. This hands-on experience deepened their understanding of celestial mechanics and the intricate movements of the heavens. For a scholar, the astrolabe was a constant companion, allowing them to verify theories, make their own observations, and contribute to the growing body of astronomical knowledge. Teachers could use it to demonstrate complex concepts of spherical geometry and trigonometry in a concrete way, turning abstract ideas into tangible movements. A student holding an astrolabe could feel the gears of the cosmos turning in their hands. Second, the astrolabe was a powerful timekeeping device. Forget rough estimates or waiting for church bells. With an astrolabe, a learned person could determine the exact time, day or night, by observing the sun or a specific star. This precision was revolutionary for scheduling prayers, timing experiments, or simply organizing daily life in an era before mechanical clocks were widespread. For universities, which were just beginning to formalize schedules, the astrolabe offered a way to mark time with a level of accuracy previously unknown outside of specialized astronomical observatories. A professor could announce the precise hour of a lecture based on astrolabe readings, bringing a new level of order to the scholarly day. Third, and perhaps most dramatically, the astrolabe transformed navigation. While often seen as a land-based tool, it was a direct ancestor of later navigational instruments, like the mariner's astrolabe. By determining latitude from the height of the pole star or the sun at noon, sailors could venture further from shore with greater confidence. This newfound ability to pinpoint one's position on the vast ocean-fueled exploration and discovery, which in turn demanded more accurate maps and a deeper understanding of geography. Learning about the world became intertwined with learning about the stars. Merchants and explorers needed to understand how to use these tools, creating a new class of educated navigators. The astrolabe was a bridge between the classroom and the open sea. The astrolabe also spurred advancements in mathematics. To design and build an astrolabe required sophisticated knowledge of geometry, trigonometry, and even early forms of calculus. To use it effectively, one had to understand how mathematical principles translated into the physical world. The process of calculating settings for different latitudes and understanding the projections of the celestial sphere onto a flat plate was an exercise in advanced mathematical thinking. Scholars studying the astrolabe found themselves pushing the boundaries of mathematical understanding. Textbooks on the astrolabe, like those by the English scholar Geoffrey Chaucer in the late 14th century, were not just manuals. They were lessons in practical mathematics and astronomy, written in a clear, accessible way to teach young students how to master this incredible instrument. Chaucer even wrote his treatise on the astrolabe for his young son Lewis, indicating how this complex tool was becoming part of the educational curriculum for the curious and well-off. Presence of astrolabes in medieval Europe, particularly in universities, indicated a shift towards empirical observation and the practical application of scientific knowledge. While many scholars still grappled with philosophical questions, the astrolabe provided a concrete way to test and verify theories about the cosmos. It was a tool that encouraged active inquiry, observation, and measurement, laying important groundwork for the scientific revolution centuries later. The intricate craftsmanship involved in creating these devices also fostered a culture of skilled artisans who understood precision and the interplay of scientific principles with practical construction. Blacksmiths and metalworkers, often working closely with scholars, became crucial partners in the advancement of knowledge. The astrolabe was not just an invention. It was a catalyst, pushing people to learn more, question more, and reach further into the mysteries of the universe. It encouraged a hands-on approach to learning, turning abstract ideas into tangible experiences. A student could literally hold the heavens in their hands and begin to unlock their secrets. Number 2. Mechanical clock. Before the invention of the mechanical clock, time was a far more fluid concept. People relied on the sun's arc across the sky, the rhythmic crow of a rooster, or the tolling of church bells to mark the passing hours. These methods were imprecise and varied wildly from place to place. Sundials only worked on sunny days. Water clocks, called clepsydrae, were used in ancient times and through the early Middle Ages, slowly dripping water from one vessel to another, but they could freeze in winter or become clogged. Hourglasses offered a way to measure specific durations, but they required constant flipping and reset. For a monk in a monastery, the call to prayer might come at the first hour of daylight, a time that changed with the seasons. For a merchant, business hours were dictated by the natural light. Learning, too, was often unstructured by exact time, relying on the natural rhythm of the day. A lecture might begin around midday, but precision was not a given. Then, in the late 13th century, a groundring invention began to emerge in Europe: the mechanical clock. We do not know the exact inventor, but around the 1280s and 1290s, large weight-driven clocks started appearing in monasteries and public buildings. These early clocks were not elegant wristwatches. They were massive machines, often built into towers, with intricate gears and a verge and foliate escapement mechanism that controlled the release of power from a falling weight, allowing for a remarkably consistent tick-tock motion. Records show that churches in England, like Exeter Cathedral, and towns in Italy, such as Florence, were among the first to acquire these complex instruments. These monumental clocks were wonders of their age, drawing crowds to marvel at their intricate workings and the precise sound of their chimes. The impact of the mechanical clock on learning was profound, even if it wasn't immediately obvious. First, it standardized time. For the first time, people across a city or even a region could agree on what noon truly meant or what 2 o'clock signified. This had an enormous effect on institutions of learning, particularly the nascent universities. Before clocks, lectures and academic discussions might start when the natural light was good or when a sufficient number of students had gathered. With the advent of precise timekeeping, universities could establish fixed schedules. Imagine the chaos of students and professors trying to coordinate their day without a shared understanding of time. Now, a bell linked to a mechanical clock could chime, signaling the precise start of a lecture on logic or theology. Students could plan their study time with greater accuracy, knowing exactly when their next class would begin or end. The mechanical clock became the silent rhythm section of the university day, ensuring that every hour was utilized effectively. Second, the mechanical clock fostered a new way of thinking about time itself. It transformed time from an amorphous natural flow into a measurable, quantifiable entity. This shift had deep implications for science and mathematics. Scientists began to think about experiments in terms of precise durations. Astronomers, already grappling with the complexities of celestial movements, now had a tool that could measure the passage of minutes and hours with a new level of accuracy, aiding their observations and calculations. The very concept of regularity and precision became ingrained in the intellectual life of the period. Historians often point to the mechanical clock as a driving force behind the systematic, measured approach that became central to scientific inquiry. The precise gears and mechanisms of the clock also inspired engineers and inventors, leading to further innovations in machinery and measurement. Learning became less about rough estimates and more about exact data. Third, the visual presence of public clocks in town squares and cathedrals served as a constant reminder of organized time. They became symbols of civic order and intellectual advancement. People would gather to watch the intricate mechanisms, fostering a general curiosity about how complex machinery worked. This widespread exposure to a precise instrument encouraged a more analytical mindset. A child growing up with the steady chimes of a town clock would develop a different relationship with time than one who lived purely by the sun. Clock was a visible emblem of progress, encouraging observation and a quest for accuracy in all aspects of life, including learning. It provided a framework for a more disciplined approach to study and research. Fourth, the construction of these complex clocks themselves became a new field of knowledge. Clockmakers were not just artisans. They were applied mathematicians and engineers. They had to understand gearing ratios, the principles of pendulums. Even though pendulums came later, the desire for greater accuracy spurred their development, and the mechanics of escapements. The knowledge required to build and maintain these devices was passed down through apprenticeships, but it also drew upon principles taught in universities, connecting theoretical mechanics with practical application. Learning about the clock became a way to understand the very fabric of applied physics. The intricate gears and springs of a clock became a metaphor for the intricate workings of the universe, leading to a new way of conceptualizing natural processes. The mechanical clock, therefore, was not merely a timekeeping device. It was a silent revolution that brought order, precision, and a new dimension of thought to the medieval world. It shaped the rhythm of universities, encouraged scientific accuracy, and subtly redefined humanity's relationship with time itself. It was a foundational piece that allowed for the more coordinated, systematic pursuit of knowledge that would characterize later eras. A student, once accustomed to the chime of the university clock, would find it hard to imagine a world without its precise guidance, marking the hours for study, debate, and discovery. Number 3. Arabic numerals and algebra. Before the introduction of Arabic numerals, European mathematics was largely stuck with the clunky and cumbersome Roman numeral system. Try multiplying Klexii by XV in your head, or even on paper. It is a nightmare. Roman numerals had no concept of place value, meaning the position of a symbol did not affect its value in relation to others, and crucially, they had no symbol for zero. Calculations were incredibly difficult, often requiring a physical abacus or counting boards, which made complex arithmetic the domain of highly specialized scholars or merchants. Even simple addition and subtraction were laborious, and anything more advanced, like long division or fractions, was a monumental task. The system severely limited mathematical progress, acting like a heavy anchor on the ship of knowledge. Learning arithmetic was a process of memorizing rules for moving counters rather than understanding abstract numerical relationships. Then, from the East, came a numerical revolution that would change everything. The system we use today, with its 10 digits from 0 to 9, originated in India. It was then embraced and perfected by scholars in the Islamic world. Around the 9th century, the Persian mathematician Muhammad ibn Musa al-Khwarizmi wrote a seminal book titled Al-Kitab al-Mukhtasar fi Hisab al-Jar wal-Muqabalah, which translates roughly to the compendious book on calculation by completion. This book introduced the world to systematic methods for solving linear and quadratic equations, giving us the very word algebra from its titles, Al-Jaba. Al-Khwarizmi's work not only showed how to use these new numbers, but also how to solve complex problems through logical step-by-step processes. These new numerals and the concepts of algebra began to trickle into Europe through trade routes and the intellectual exchanges in places like Islamic Spain. The most influential figure in their widespread adoption was an Italian mathematician named Leonardo Fossomai from Pisa. In 1202, Faidai published his groundbreaking book, Liber Abaci, which means the Book of Calculation. In this book, he explained the Hindu-Arabic numeral system, including the concept of zero as a placeholder, and demonstrated its immense power for arithmetic operations. He showed how addition, subtraction, multiplication, and division could be performed with ease and efficiency. Using these new symbols, Faithamu's book was a revelation. It was clear, practical, and immediately showed the superiority of the new system over Roman numerals and the abacus. The impact on learning was immediate and due. First, calculations became vastly simpler and faster. Imagine a student learning mathematics. Instead of laboriously manipulating counters on an abacus or wrestling with Roman numerals, they could now perform complex multiplications or divisions with pencil and paper. This ease of calculation liberated mathematicians from tedious labor, allowing them to focus on deeper theoretical problems. Counting, trade, and engineering also saw massive improvements. Merchants could balance their books with greater accuracy and less effort. Architects could calculate dimensions with new precision. The financial world began to operate on a completely different level. Second, the introduction of zero was a game changer. Zero is not just a digit. It is a profound philosophical and mathematical concept that allows for positional notation. In a system like 205, the zero indicates that there are no tens, but its presence pushes the 2 into the hundreds place. This seemingly simple idea made complex numbers manageable and opened up possibilities for abstract thought that were impossible with Roman numerals. Concept of nothingness, when given a concrete symbol, became a powerful tool for describing and manipulating quantities. It allowed for the development of infinitely large and infinitely small numbers, fundamental to later calculus. Third, algebra, with its use of symbols to represent unknown quantities, introduced a new way of thinking about problems. Instead of just calculating specific numbers, algebra allowed scholars to formulate general rules and relationships. This abstract approach was crucial for the development of all modern sciences. When you can describe a problem using variables and equations, you can solve entire classes of problems, not just individual instances. This enabled astronomers to predict planetary movements with greater accuracy, engineers to design more stable structures, and physicists to describe the laws of motion. Learning to think algebraically meant learning to think in terms of universal principles. It was like unlocking a new language for describing the universe. Fourth, the accessibility of these new methods meant that mathematical knowledge could spread beyond a tiny elite. While not everyone became a master mathematician overnight, the tools were there for more people to learn and apply arithmetic. Universities began incorporating these new methods into their curricula, gradually replacing the old cumbersome systems. Students learned about algorithms, a term derived from Al-Khwarizmi's name, for solving problems systematically. The widespread adoption of Arabic numerals fostered a more literate and numerate society, providing the essential tools for the scientific and technological advancements that would characterize the Renaissance and beyond. The very act of writing down numbers became a clearer, more logical process, allowing for fewer errors and greater understanding. This mathematical revolution laid the groundwork for everything from modern finance to computer science, all because of a set of 10 simple symbols and the revolutionary concept of zero. Number 4. The university. Before the rise of the university, learning in Europe was quite different. Knowledge often resided within monastic schools, tucked away in quiet cloisters where monks copied ancient texts and studied theology. There were also cathedral schools, attached to major churches, which taught clergy and a few privileged lay students. Beyond these, individuals sometimes learned through apprenticeship or by seeking out famous scholars who taught informally in their homes or in public spaces. Students often traveled great distances to sit at the feet of a particular master. But there was no formal structure, no common curriculum, and no standard way to earn recognition for one's learning. It was a fragmented landscape with knowledge unevenly distributed and without a centralized hub for its production and dissemination. There were no degrees, no faculties, and no student services. Then, starting in the 11th and 12th centuries, a completely new institutional model emerged: the university. It wasn't invented by one person, but rather grew organically from these existing schools and from the demand for more organized professional learning. The first true universities appeared in places like Bologna, Italy, where students gathered to study Roman law, and Paris, France, which became famous for its theology and liberal arts. Other early examples include Oxford and Cambridge in England and Salerno in Italy, known for its medical studies. These institutions were revolutionary because they brought together students and masters into a formal community organized around specific fields of knowledge. The university as an invention revolutionized learning in several critical ways. First, it formalized the curriculum. Instead of individual scholars teaching whatever they wished, universities established structured courses of study. For example, a student at the University of Paris would typically begin with the Faculty of Arts, studying grammar, rhetoric, logic, arithmetic, geometry, astronomy, and music, known as the 7 liberal arts. Only after mastering these foundational subjects could they move on to higher faculties like theology, law, or medicine. This systematic approach ensured a comprehensive education and a common intellectual framework for all graduates. Scholars today, studying medieval university records, find detailed lists of prescribed texts and topics showing the rigor of the curriculum. Second, universities professionalized learning and teaching. Masters were no longer just individuals with knowledge. They became licensed professors, often holding debates and delivering formal lectures. Students in turn worked towards degrees, the Bachelor of Arts, Master of Arts, and eventually doctorates, which were recognized across Europe. These degrees certified that a person had achieved a certain level of mastery in their field, providing a credential that opened doors to careers in the church, law, medicine, or government. The university created a clear pathway for intellectual advancement, transforming education from an informal pursuit into a recognized profession. A student could realistically aim for a career built entirely on their learning. Third, universities became centers of knowledge, creation, not just transmission. While copying and preserving ancient texts remained important, scholars at universities engaged in active intellectual inquiry, debating complex philosophical and theological questions, and developing new ideas. The disputation, a formal academic debate where students and masters would argue different sides of an issue, was central to this process. It sharpened critical thinking skills and pushed the boundaries of existing knowledge. These debates were often highly spirited affairs, drawing crowds of curious onlookers. New works of scholarship, like the Summa Theologica by Thomas Aquinas at the University of Paris, emerged from these vibrant intellectual environments. Scholars at these institutions were not just memorizing. They were analyzing, synthesizing, and innovating. Fourth, universities fostered the growth of scholarly communities. Students and masters from different regions and backgrounds gathered in one place, creating a vibrant melting pot of ideas. They formed nations or guilds within the university for mutual support and protection, reflecting the diverse origins of their members. This intellectual camaraderie led to the exchange of ideas across linguistic and national boundaries. A student from England might share lodging with a student from Italy, both studying Latin texts but bringing their own regional perspectives to the table. This cross-cultural dialogue was crucial for the spread of knowledge and the development of a shared European intellectual identity. Professors would often travel between different universities, bringing their knowledge and teaching styles to new audiences, further spreading ideas. Finally, universities often developed their own libraries, which became massive repositories of knowledge. These libraries were meticulously organized and contained vast collections of manuscripts, often painstakingly copied by student scribes or hired professionals. Access to these resources was invaluable for scholars undertaking research and for students delving into complex texts. The university library became a physical manifestation of accumulated wisdom, a place where all learning could converge. The rules for using these libraries were often strict, reflecting the immense value placed on the books within them. The medieval university, therefore, was not merely a building. It was an organizational and intellectual invention that fundamentally reshaped how knowledge was created, disseminated, and certified. It laid the groundwork for modern higher education and became a powerful engine for intellectual progress, giving structure and purpose to the pursuit of learning. Turned the pursuit of knowledge into an organized, powerful force that would profoundly impact the entire world. Number 5. Eyeglasses. Imagine being a brilliant scholar in the 13th century. You've spent decades poring over ancient texts, writing commentaries, and debating profound philosophical questions. You are at the height of your intellectual powers. But then, a cruel trick of nature begins to play out. Tiny script on the manuscripts, once so clear, starts to blur. The delicate lines of the illuminated letters merge. Reading, your life's passion and profession, becomes agonizingly difficult, then impossible. Your scholarly career, for all intents and purposes, is over, simply because your eyes can no longer focus on nearby objects. This was the fate of countless learned individuals before the late 13th century, as presbyopia, or age-related farsightedness, inevitably set in. Scribes, lawyers, merchants, and anyone whose livelihood depended on close-up vision faced this frustrating reality. Their knowledge, once so sharp, became locked behind failing eyesight. Then around the very end of the 13th century, specifically between 1286 and 1290, something truly extraordinary happened in northern Italy. The exact inventor is debated, with figures like Salvino d'Armate and Alessandro della Spina often mentioned in early accounts. But what is clear is that the first eyeglasses appeared. These were not sophisticated modern spectacles with ear hooks. They were typically convex lenses, ground from quartz or beryl, set into frames of bone, metal, or leather. They were usually held up to the eyes or balanced on the nose, sometimes even held in place by a craftsman's forehead strap. A document from 1289 in Florence mentions a legal secretary who found it impossible to read or write without the new spectacles. This simple invention, 2 pieces of curved glass, would revolutionize the intellectual landscape of Europe. The impact of eyeglasses on learning was immediate and immense. First, they extended the working lives of scholars, scribes, and intellectuals. Before eyeglasses, a scholar might be forced into early retirement from close work by the age of 40 or 50. With convex lenses, their reading and writing careers could continue for many more decades. Imagine the sheer volume of knowledge that could be produced, copied, and studied by individuals who are now able to work well into their 60s and 70s. The productivity of universities, monasteries, and legal chambers dramatically increased. Older, more experienced scholars, who had accumulated vast amounts of wisdom, were no longer sidelined by vision problems. They could continue to contribute their insights, mentor younger students, and participate in intellectual debates. One example, documented by historians, is that of the Venetian nobleman and statesman Marco Polo, not the famous traveler, who in 1311 wrote that he would not be able to read or write without his glasses, emphasizing their crucial role in his continued work. Second, eyeglasses fundamentally changed the economics of knowledge production. Scribes, whose meticulous work involved copying entire books by hand, could now work longer hours with less strain and fewer errors. This increased efficiency, though still slow by modern standards, helped to slightly reduce the cost of books and make more copies available. While books remained expensive until the printing press, the steady supply of scribes able to work productively was vital for maintaining the flow of written information. Lawyers could read complicated legal documents, merchants could scrutinize ledgers, and administrators could process countless charters and decrees. This allowed for greater accuracy and efficiency in all professions requiring close reading. Third, the availability of eyeglasses indirectly fostered a culture of deeper textual engagement. If reading was no longer an exhausting and physically demanding task, people could spend more time with texts, delve into more complex arguments, and make more detailed annotations. Scholars could compare multiple manuscripts, spot inconsistencies, and develop more nuanced interpretations. This increased facility with text was essential for the intellectual developments of the late Middle Ages, leading to new philosophical insights, legal codes, and scientific observations. The act of reading became less of a struggle and more of a pleasure, encouraging more people to engage with written knowledge. Fourth, the invention of eyeglasses also brought a new appreciation for the practical application of scientific knowledge, particularly optics. Grinding lenses required a precise understanding of glass, light, and geometry. Artisans who could create effective lenses gained new respect and status. This practical expertise fed into the burgeoning scientific curiosity of the era. The technology of lens making continued to advance, laying the groundwork for later inventions like the telescope and microscope, which would dramatically expand humanity's ability to see both the very distant and the very small. The simple, curved glass of the medieval spectacle was a tiny, powerful window into a larger world of scientific inquiry. The impact of eyeglasses is sometimes overlooked because they were not a grand public invention, like a cathedral clock. But their quiet revolution transformed the personal, intellectual lives of countless individuals. They unlocked a new era of productivity for the learned, allowing wisdom to flourish and accumulate for longer periods within the minds of those who possessed it. For any scholar struggling to read the fading ink of an old manuscript, a pair of carefully ground lenses was nothing short of a miracle, a gift that returned the world of knowledge to their grasp. Number 6. Paper. For much of the early Middle Ages in Europe, the primary material for writing was parchment, also known as vellum. This was animal skin, usually sheep, calf, or goat, that had been meticulously prepared. To make parchment, animal hides had to be soaked in lime solutions, scraped clean of hair and flesh, stretched tight on frames, and then painstakingly smoothed with pumice stones. This process was incredibly labor-intensive, time-consuming, and expensive. One large book could require the skins of dozens or even hundreds of animals. As a result, books were rare and precious objects, affordable only by the wealthiest monasteries, churches, or royal courts. Learning was often oral or dependent on these costly, scarce manuscripts. Students typically could not afford their own books and relied on rote memorization or borrowing. Even common administrative records or personal letters were limited by the high cost of writing material. The very act of writing was a luxury, a testament to the value of the information being recorded. Then came paper, a material that had a much humbler origin and a far more efficient production method. Paper originated in China during the Han Dynasty, around 105 CE, where it was invented by a court official named Kai Lun. His method involved using mulberry bark, hemp, old rags, and fishing nets, pounding them into a pulp, pressing the pulp into thin sheets, and drying them. This innovation spread across Asia, eventually reaching the Islamic world in the 8th century. A pivotal moment occurred in 751 CE during the Battle of Talas, where Arab forces captured Chinese papermakers, bringing their secret knowledge westward. Paper mills soon sprang up in cities like Samarkand and Baghdad, producing vast quantities of paper from rags and other plant fibers. The Islamic world embraced paper, using it for everything from religious texts to scientific treatises, administrative documents, and even paper money. From the Islamic world, paper slowly but surely made its way into Europe. The first paper mills in Europe were established in Islamic Spain, particularly in Jativa, around the 10th century. From there, the technology spread to Christian Spain and then to Italy, with the first major Italian paper mills appearing in Fabriano in the 13th century. By the 14th and 15th centuries, paper production was becoming more widespread across Europe. The key difference was that paper was made from readily available materials, primarily linen rags, which were a byproduct of the textile industry. Process, while still requiring skill and machinery, was significantly faster and cheaper than producing parchment. The impact of paper on learning was revolutionary in many ways. First, it drastically reduced the cost of writing materials. This was a monumental shift. Suddenly, books, though still copied by hand for centuries, became more affordable and accessible to a wider range of people. Monasteries and universities could acquire more texts for their libraries. Scholars could afford to buy or commission copies of important works. This increased availability of written material led to a greater spread of knowledge and a general rise in literacy. For the first time, a moderately wealthy student might own a small personal library rather than just relying on the few precious books in the university library. Second, paper made information more disposable and easier to produce in quantity. While precious parchment was reserved for official documents and grand tomes, paper was perfect for everyday use. Students could take notes during lectures, copy down passages for their own study, and sketch out ideas without worrying about the cost of the material. This fostered a culture of personal note-taking, experimentation, and independent study. Lawyers could produce multiple copies of legal briefs, merchants could keep detailed ledgers and correspondence. Governments could issue decrees and collect taxes more efficiently. The sheer volume of written material in circulation exploded. Historians studying medieval archives notice a clear shift from parchment to paper for administrative records as paper became more available, indicating its practical advantage. Third, paper supported the growth of new educational methods. With cheaper paper, it became practical to produce paya systems in universities. Pekya was a section of a book rented out to scribes or students for copying. This decentralized copying process allowed for the rapid multiplication of texts, ensuring that many students could have access to the same material simultaneously. This system helped to standardize the curriculum across different student groups and fostered a more efficient way of learning. The ability to copy large sections of a text quickly was a significant boon for students. Fourth, paper's widespread use paved the way for the ultimate revolution in learning, the printing press. While the printing press could theoretically have used parchment, its true potential was unlocked by the availability of cheap, consistent paper. Imagine trying to print 180 copies of a Gutenberg Bible on animal skins. The sheer scale would have been impossible. Paper provided the perfect medium for mass production, absorbing ink well and being relatively easy to produce in large sheets. Without paper, the printing press would have remained a limited curiosity, unable to transform learning on a global scale. In essence, paper democratized information. It took knowledge from the exclusive realm of the very rich and powerful and began to place it, piece by piece, into the hands of more ordinary people. It was a silent revolution, a humble material that enabled profound changes in how people learned, communicated, and managed their world. It was the unsung hero that made the later explosion of printed knowledge possible. Number 7. The printing press, Gutenberg. Before the middle of the 15th century, the creation of books was a painstaking and often error-prone process. Every single book was copied by hand, typically by scribes working in monasteries or in scriptoria associated with universities. These scribes, often working for years on a single large text, would meticulously pen each letter, line by line, page by page. The ink was made from soot and glue, the pens from goose quills, and the writing surface was expensive parchment prepared from animal skins. Each copy was a unique work of art and immense labor. As a result, books were incredibly rare, incredibly expensive, and incredibly slow to produce. A university might have only a few hundred books in its entire library. Scholars had limited access to texts, and identical copies were almost non-existent, as scribes inevitably introduced small errors or variations. Learning was confined by the scarcity of written materials. A single mistake by a scribe could propagate through countless later copies, hindering the spread of accurate knowledge. Then, around the 1440s to 1450s, in the city of Mainz, Germany, a goldsmith named Johannes Gutenberg brought together several existing technologies in a completely new way. He didn't invent printing itself. Woodblock printing had existed in China for centuries, and even some crude metal block printing was known in Europe. But Gutenberg's genius lay in perfecting the system of movable type. He developed a method for casting individual letters, numbers, and punctuation marks from metal alloys, using molds that allowed for incredibly precise and consistent typefaces. These individual pieces of type could be arranged to form words and sentences, then inked and pressed onto paper using the modified wine press. After printing, the type could be broken down and reused for new pages. This combination of movable metal type, an oil-based ink suitable for printing, and a mechanical press was the true innovation. The impact of Gutenberg's printing press on learning was nothing short of revolutionary, shaking the very foundations of how knowledge was produced, distributed, and consumed. First, the printing press dramatically increased the speed and volume of book production. What took a scribe months or years to copy, the press could produce in days. The Gutenberg Bible, finished around 1455, is the iconic example. It was a massive undertaking, but Gutenberg produced approximately 180 copies, a staggering number for the time. This explosion in quantity meant more books were available than ever before. Libraries expanded rapidly, and individual scholars, merchants, and even wealthy commoners could begin to acquire their own personal collections. The sheer availability of books meant that more people had access to the written word, fueling a thirst for reading and knowledge. Price of books dropped considerably, making them more attainable for a wider segment of society. Second, the printing press standardized texts and reduced errors. Before printing, every manuscript copy of a work was slightly different, prone to scribble mistakes, intentional alterations, or misinterpretations. With the printing press, once a master copy was proofread and set in type. Every subsequent copy produced from that type was identical. This ensured a consistent and reliable version of a text, which was crucial for scholarly debate and the accurate transmission of knowledge. Scholars could now refer to specific page numbers or lines, confident that others with the same printed edition would see the exact same words. This uniformity was vital for the development of modern scholarship and the scientific method, where precise data and consistent information are paramount. Textual criticism. Once a battle against variant readings, became a study of authorial intent. Third, the printing press fueled the spread of literacy. With more books available and at lower prices, there was a greater incentive for people to learn to read. Education began to extend beyond the clergy and the nobility. Merchants, artisans, and professionals in towns and cities eagerly sought out printed materials, from practical guides to religious texts and popular literature. This rising tide of literacy created a larger audience for new ideas and discoveries. Pamphlets and broadsides could be printed quickly and disseminated widely, carrying news, religious tracts, and political commentary. Press didn't just print books, it printed information in every imaginable form, reaching every corner of society. Fourth, the printing press democratized knowledge and challenged traditional authority. Before printing, knowledge was largely controlled by the church and by elites who owned the few existing books. The printing press broke this monopoly. Ideas, even controversial ones, could now spread rapidly and widely, bypassing the gatekeepers of information. The Reformation, for example, would have been impossible without the printing press. Martin Luther's 95 Theses and other writings were printed and distributed across Europe with astonishing speed, allowing his ideas to reach a mass audience and spark widespread debate. This widespread dissemination of diverse viewpoints encouraged critical thinking and independent inquiry, leading to profound social and intellectual changes. The printing press was a powerful tool for intellectual freedom. Fifth, the printing press allowed for the rapid dissemination of new scientific discoveries and inventions. When Galileo discovered the moons of Jupiter, or Vesalius, published his detailed anatomical drawings, their findings could be printed and distributed to scholars across Europe within months. This accelerated the pace of scientific progress, allowing researchers to build upon each other's work much more quickly. Illustrated books became possible, combining text with detailed images, which was particularly important for fields like anatomy, botany, and engineering. A scientist in Florence could read the exact observations of a scientist in London, leading to a truly collaborative European intellectual community. The printing press, therefore, was not merely a mechanical invention. It was a cultural and intellectual earthquake that transformed the landscape of learning forever. It moved knowledge from the exclusive realm of the few to the potential grasp of the many, fostered critical thinking, and set the stage for the Renaissance, the Reformation, and the scientific revolution. It was the ultimate medieval invention for learning, making the vast ocean of human knowledge accessible to all who dared to dip their toes in its waters.